This class is one of a series on introductory talks to operations management. As I said, there are several videos in this series, and you should really make every effort to look at all of them. Remember to make notes as you look at them, stop the videos, wind it backwards, wind it forwards, make your own notes, and pad out your notes from reading as well. In this particular class, we're going to deal with modeling and focus in on the importance of modeling. Now, for a start, modeling is trying to look at a whole system through the eyes of a small model which can illustrate problems that may arise or issues that may arise when the full system is put in. So it's a scaled down version of the full system. It doesn't have to be physical, as we'll see. It could be mathematical, or it could be descriptive in some way. So it doesn't have to be a physical model, but it could be a physical model. It could be a model set out on the top of a workbench that illustrates the issues that may be encountered when full production takes place using machines and warehousing facilities and so on. So modeling is important. It gives a picture of what may happen when the full system is brought to bear. And it's widely used in engineering. Often when people are building a ship, they will first build a model of the ship, and they will test the model to see what are its properties and so on. The same with aircraft, the same with many products. People want to see what it looks like. They need to have it modeled. More and more, of course, this has been done on computer with computer aided design packages. CAD packages are used, and full rendered models, almost like pictures of the real thing, may be presented on the computer monitor and rotated and changed and so on. So modeling is very important. It's a way of seeing the full system, but at the same time only using a scaled down version, a cheaper, obviously much cheaper scaled down version. So the use of models, well, we could have prototypes, as I said, a physical model. Sometimes when companies are asked to produce a new product, they will produce a prototype and show it to the customer. And if the customer approves, it meets the customer requirements, then it could go into full-scale production. But it may start as an example, a specimen, a prototype, which is shown to the customer, or it may be also used for training purposes, shown to the workers, to the personnel who will perhaps be involved in the manufacturing or the production of this particular item. So the prototype serves as an example. But could also be schematic models, graphs, charts, pictures. It doesn't have to be physical, as I said earlier. It could be a pictorial representation of what the product should look like, or what should be done, or it's the use of perhaps visual aids as opposed to a physical product. Sometimes mathematical models could be used, as I said earlier. For example, statistical models. So when production has been designed, it may be possible to work out what the schedules will look like in advance using statistical models, using estimates of times on particular machines, the sequencing of the machines, the handover times, so that some sort of statistical model allowing for errors, allowing for variations to some extent, but try to be as realistic as possible. That sort of quantitative approach may be useful in looking at the overall efficiency of a system. There are also inventory models. There's one video class on stock control, which illustrates the theoretical quantity that should be ordered, economic order quantity, and gives a formula for it, and it's one of the videos on the course. That is, if you like, a theoretical model, but it serves as a backdrop to what happens in practice. It shows the ideal amount that should be ordered for inventory purposes. But perhaps because of all sorts of issues, constraints on the supplier side, capacity of the stores and so on, perhaps the most rational amount to be ordered can't in fact take place. But inventory models are used to show how the stocks should be ordered, the sequencing, the time of the orders, the delivery times, processes within the stores itself, moving stock from one position into a position where they will be used fast. It could be that a Kanban system is used. That's the subject of yet another video on the course. But all sorts of issues can be imagined, and models can be created, and models can be experimented with as well. What will happen? What if this happens? What will happen then? And look at the model and try and see what would actually follow if that what if happens. What will the outcome be if the deliveries don't take place on time? What will happen? What if? It could be sometimes people use very sophisticated mathematical models to solve particular problems. For example, linear programming may be used. There are constraints and there's an objective function. The objective function is to, let's say, maximize the throughput of the production system, maximize the amount that's been produced. Well, the constraints are the number of machines, the number of workers, the capacity of the stores. There are many constraints that may be taken into account, and the amount produced will be determined by the value of the constraints. But what exactly the amount should be can be calculated using linear programming. In fact, there are other programming techniques which may be used. Non-linear programming, for example. Perhaps some elements in the production process don't follow linearity. It could be as more of one is produced, the system becomes more efficient at producing it. Now, that's not a linear relationship, it's a non-linear relationship. Or it could be we have integer programming. Sometimes the ideal amount to be produced is 25.5, let's say. Well, that's fine, but if you're producing 25.5 boats, if you're in the boat manufacturing business and producing boats for sailing clubs, well, producing 25.5 doesn't make any sense. The half boat will not perform very well. It'll sink. So originally linear programming was developed at the end of the Second World War by George Danzig in the American Air Force. But since then it's been developed on to look at non-linear programming techniques and integer programming and so on. So very sophisticated models can be used. And I say very sophisticated. In fact, nowadays on something like Microsoft Office using Excel, the spreadsheet, it's possible to work out linear programming solutions. So the progress that computing technology has made has brought a lot of these techniques now within the reach of operations managers, who can now get very sophisticated mathematical techniques to help them in the decision-making process, and they can get them very cheaply. Perhaps in the past it would mean involving consultants and perhaps buying expensive software and even upgrading the computers. But more and more of these are becoming available in fairly standard packages. Could be queuing techniques. Queuing techniques, again, these were developed to try and handle situations where bottlenecks and queues develop. It depends on the number of channels, the number of access points, and so the rate at which people are joining the queue and the rate at which people are being served, let's say in a bank, that will determine the length of the queue, let's say in a banking situation. But you have queuing in business. You have machines. You have jobs queued up waiting to go onto a particular machine. Perhaps if the feeding machines, the machines that are feeding the work to another machine, if they are running at full capacity, perhaps the machine that comes next will be overwhelmed in a sense. It'll have a lot of jobs waiting to be done. Well, decisions have to be made by the operations management then as to whether to acquire another machine or to work that machine longer. But then, of course, they're running the possibility of breakdown, and the machine will wear out faster. So decisions have to be made. All of these decisions are quite difficult. But there are project management models that crop up in the literature that try to help in the decision-making process. But because production is so variable, you can have companies producing boats, as I said earlier, or they may be producing nuts and bolts. They may be producing nails or whatever. They might be producing furniture. Because the number of products is so variable, it's difficult to have a standard project management model. You have ideas about how to do it, and these ideas will be based on particular models that are looked at by project management, but they vary. They vary from company to company, mostly because of the product and the nature of the product and the requirements of the product. So what types of models? Well, there are simulation models. These are used to test a proposed idea. It's simulated. It's not done, it's just simulated. It could have a computer that simulates the problem to see if it is possible, if there are any unforeseen issues that's going to arise. If it works, if you like, in theory, then hopefully it'll work in practice. If it works, let's say, on a computer, then and it's adequately discussed amongst experienced staff, then the chances are it'll work in practice. There are techniques, for example, the Monte Carlo technique, which is based on probability. The name Monte Carlo should suggest probability. But here models are developed showing the relationship between inputs and outputs, and inputs onto one machine, onto the next machine, and so on, and the probability of failure and the probability one machine will go slower than the next machine, and then trying to work out the probabilities. All the probabilities add up to 1, of course. Work out the probability that the customer will be satisfied at the end. So I'm not getting into the Monte Carlo simulation technique here, but I'm just saying it's available, and it's one that sometimes may be used. We also have optimization models. These are designed to create an idea of the optimal way to go about the task, the best way to go about it. The idea of working out the best output and the best configuration of the production facilities to, if you like, maximize efficiency. And one way to look at that is back to linear programming. That is the most probably most widespread use of an optimization technique. But optimization techniques are widely used as well in mathematics. It's possible to conceive of, let's say, a mathematical function and say, instead of finding the maximum of that function, we can't find the maximum because there is some constraint. So now it's finding the maximum subject to the constraint, finding the best subject to that constraint. And there are techniques in mathematics that can be used to help out there. One springs to mind is called the Lagrangian multiplier, but that's something we don't deal with here. But the point I'm trying to make is that optimization models may be used to try and maximize the throughput of the system. Sometimes models may be pattern recognition models, trying to work out what happened in the past, what was the experiences in the past, what happens if some aspect of the production system was varied, what happened as a consequence. Is there a pattern to what happened? Is there a pattern in the way the system works? And try to recognize the pattern, and from that get some insight into what is the best way to proceed. Of course, pattern recognition models are ideally suited for management who have experience, who have worked with the machines, who have worked in situ, and know the ups and downs of the particular production system. That type of management will be able to recognize patterns more quickly than others, or quicker than others, I should say. And they will be able to work out more rational ways of working as a consequence of their recognizing patterns. So patterns may be variations in the machines, and if the machines are working at peak capacity, the pattern is that in the past the machine will break down, or other machines will not be able to keep up, or there will be bottlenecks further in the production system, or whatever. These are the patterns based on experiences from the past. So part of the pattern recognition model system might be looking at statistics from the past, looking to see if there are patterns in the throughput, the amount of work that was undertaken and successfully completed by the production system, looking at the variations in the statistics, talking to the experienced managers, as I just said, getting a feel for what the system can take, and forecasting, trying to forecast that if orders of a certain quantity were to come in for a certain line of output, does the system have the capacity to deal with that? And that might be looking at pattern recognition in more detail to say, well, in the past when we had big orders, the following parts proved to be a problem, and those are the parts now that need to be addressed. The parts could be the stores were unable to deliver the raw materials in a timely fashion, or the suppliers to the stores were unreliable at the time, and orders were received late, or whatever. And data mining is a term that's often used. Data mining means trying to find the information, dig out the information from wherever it is. It could be experiences from other companies, perhaps sometimes experiences that have been published online, or there may be forums online related to a certain product or a certain material, and trying to get as much information as possible, mining the information, trying to collect the information from a wide source. The types of models, as I said, there could be quantitative models. These are often seen as the best because they're not relying on judgment, they're not relying on people's attitudes. They are quantitative. This is what happened. So experience is almost like quantitative material, because if the experiences are reliable and if the experiences are honest, the people given their experiences, are not promoting some hidden agenda, then that is very similar to quantitative approach. We also have analysis of trade-offs. Sometimes machines can be used to produce different items. But obviously if the machine is producing one particular item, it can't produce the other one. So which one is best? Which one does the company need more urgently? This is very similar to opportunity cost that we talk about in other videos. Opportunity cost is the next best alternative that the company can't have. So if a machine is doing one particular activity, it can't do another activity. If workers are working on one sort of area of the business, they can't be working simultaneously on a different part of the business. So it's important that the operations management look into trade-offs and see what's the best course of action under different situations. Looking at the systems in total as well, looking at the production system, look at the whole system to see how efficient it is, and look at the subsystems within that. Look at the stores as a subsystem. Look at the production part of the system. Look at production as another subsystem. So you have different subsystems, and look at the efficiency of each, and see how the various subsystems link to each other, and if they are efficiently linked. So it's possible to get some sort of optimization of the overall system. The important thing to bear in mind here is that when one part of the system is under pressure, bottlenecks can develop, and these could be very costly to the business. So it's a question of carefully monitoring all of the subsystems, monitor the stores, monitor material handling, monitor the throughput on the various machines. All of that will lead to an overall optimization. Models are beneficial. They're easy to use and they're not that expensive. So using conceptual models are a good way to move forward. Even linear programming, as I said earlier, which is available on Excel and widely available now online. It's possible to enter the data and get the calculations done in a straightforward way. And the interpretation of the data is also sometimes offered as a part of the package. So models are easy to use, generally speaking, and they are a lot less expensive than setting up the whole system in practice and running it to see what the outcomes will be. Companies can't experiment like that for a start. It's too costly, and if such experiments were run, then of course actual production would not take place. So it's important that models are isolated and thought through and available to test parts of the system to see if there are any issues likely to come up. So they require users to recognize and understand the problem, to recognize and deal with the problem. Recognize it, understand it, and deal with it. Users can see what the system is or would be like from the model. So they can organize the production system based on the model, based on the experience of looking at the model and studying the model. And of course they can understand the problem. Any problems that arise, that they can see the problem from the model and they can find workarounds, they can find solutions to the problems and implement those solutions and rerun the model to see what the outcomes are likely to be under the revised model. Generally speaking, models tend to be consistent. The models don't vary a lot. There's no human element for a start, generally speaking, in the use of models. Models tend to be computer-based models, or there could be prototypes, as I said, small workups of models, depending on what the required outcome is, depending on what the product is, and depending on the resources available for this type of work. But generally speaking, models tend to be quite consistent. Sometimes actual production systems may be not that consistent because workers have good days and bad days, and sometimes the machines may be running slow or break down, or suppliers may be late in making deliveries. So there's all sorts of issues about the consistency of the overall system. But models tend to run smoothly, or can run smoothly. And it's a standardized format. It's focused in on solving a problem and studying a problem, and it's standardized. It's controlled. So the person looking at the model can vary one part of the model and then make observations about the likely consequences of that variation. So it's the whole system is not running, so it's easy to isolate out what issues there are by making adjustments perhaps just to one of the aspects of the model, one of the variables, and seeing what the outcome will be. Generally speaking, models have specific objectives. The objective is to solve a real problem, or to simulate what happens on the shop floor and give an understanding of what happens on the shop floor. But models are not really developed just for the fun of it. They are focused on some issue, and they have got an objective to try and give a better understanding of the production process, or to look at scenarios where parts can go wrong in practice and see what solutions, what plan B, if you like, can be developed to cope with those breakdowns or those issues that arise in practice. So models are a systematic approach to problem solving. It's systematic in the sense that it's studying the actual system, it's simulating the actual system, and it can try to work out rational solutions to problems. And it can do this at very low cost. The whole system is within the business can still be running, and the operations management can vary different parts of the system on the model and see what will happen, and then expect the same to happen on the full system in production if such changes were implemented there. As I said, there's an analysis of trade-offs. It's important that the management know what the trade-offs are. If more of one resource is used, then less of another resource will be available, and so on. It's important that the constraints of the system, and the constraints are what give the trade-offs in the first place. It's important that the management understand the constraints. They've only got a certain number of machines. They've only got a certain number of people. The stores are of a particular size. The suppliers have got a history of being punctual or not being punctual with deliveries, and so on and so on. So it's important that the management have a good understanding of the constraints with which they work, and have some sort of understanding of the trade-offs that can be made to perhaps get round issues if they arise. Models can be used to deal with the what-if questions. What if a machine breaks down? We'll go to the model and take out that machine and see what happens to the rest of the system. What's likely to happen? Will there be queues and build-ups, and what will happen to the final product? And so it's possible to run what-ifs. What if a new machine is purchased with extra capacity? How will that affect the overall performance of the system? What if workers are retrained in a certain technique? what will happen to output, to quality, efficiency, and so on. So what-if questions can be analyzed cheaply by the use of a model. Of course, models can bring the power of mathematics to bear on problems as well. Mathematics are a good way of getting an insight into how systems work. Looking at, perhaps at one level, just looking at statistics that are coming off, let's say, off a machine. The machine's able to produce so many items per hour if it's running at full capacity. Well, the next machine will have to run at the same speed, otherwise there'll be a build-up. Now that's a very simple mathematical relationship. If one machine's running at a certain rate, the next machine must run at the same rate to avoid queues and bottlenecks and hold-ups. So in bigger systems, it can be much more sophisticated, and much more powerful mathematics can be brought to bear. But really it depends on the nature of production, depends on the size of the business and the nature of the business. It may not be worthwhile engaging in that level of sophistication. But of course, if the business was producing aircraft or something very expensive and very complicated, then very sophisticated modeling techniques would be used, perhaps based on quite advanced mathematics. There is one little concluding bit we need to just mention here. There's something called the Pareto Phenomenon, which models can deal with and look at as well. A few factors account for a high percentage of the occurrence of some events. That's the idea. So sometimes things happen within the business. A machine breaks down, or production is slower than anticipated, and when it's traced back, they find that just a few issues, a few things are causing the problem. A few issues on perhaps one of the machines, or sometimes it's an unexpected part of the system that is now not working optimally, that's causing these high percentage failures in the system. And Alfredo Pareto, an Italian economist back in the 1930s, he came up with this idea of the 80-20 rule. 80% of problems are caused by 20% of activities. So sometimes operations management are looking for a small set of activities which can cause a lot of problems. This is known as the 80-20 rule. Again, modeling is very useful in this case. Using modeling techniques, it may be possible to isolate key activities, activities which, if they break or if they suffer some slowdown or some issues, if they behave in this way, then there are major implications further down the line, further in the production process. So that a small number of perhaps machines or a small number of workers working in a particular area, if they encounter problems, it will lead to major problems later in the production system. So a small number, 20% in Alfredo's terms, cause a large number of problems. It's not right to say that Pareto meant 80-20 literally. What he was saying was a small number of activities can cause a lot of problems. And it's better to see the 80-20 rule in that light. It's not a statistical rule. It is more a comment. It's saying a small number of activities can cause a lot of problems. So it's important that the modeling process looks at the small issues as well as the big issues, because the small issues may eventually lead to some big problems later on. That's all I want to say about modeling. Modeling is very useful. It's cheap. It gives a picture of the overall system. It can be used to make decisions. It's possible to make changes to the model to see what the outcomes are likely to be. There are different types of models, sometimes based on probabilities, Monte Carlo. Sometimes they are very rational models, such as linear programming or one of the programming techniques. Sometimes there may be prototypes, there may be physical models built. Small, very small, but proportionally the same as the production system, so that the model can be used to study the layout of the plant or study the way machines are configured or whatever. So we've got an understanding of the business, a better understanding of the business from the study of the model. And that's all I'm going to deal with in this class. So I'm going to leave it at that and say thank you for watching.